Thank you. I started.
Okay, great. Hi, everyone. My name is Suman Satel. I'm here at University of Texas at Arlington. Today, I'm chairing this Astro session. I have seven speakers from around the world. So I'm going to start with talk from Manish Khanal. Let me see if I can get his information here. Uh, or I can just. So we have Manish Khanal from Amrit campus, Tribhuvan University. He's going to talk about a comparative study of physical properties around asymptomatic giant branch star IRAS, TES in Iris, and AKRI map. So Uh, Manish, I hope you are there live listening to the talk since it's recorded. We'll have quite. It seems like video is 9 minutes 36 seconds, so it should be right on time. Okay, here goes Manish Kanal.
Thanks everyone. It's a pleasure to have you all in this presentation on my work entitled A Comparative Study of Physical Properties Around Asymptotic Giant Branch Star IRAS 01142 plus 6306 in Iris and Akari map. So the structure of the presentation is as shown here, starting with introduction. First introduction about AGB stars. When the star exhausts the supply of hydrogen by the core contracts and its temperature will increase, causing the outer layer of the star to expand and cool. Then the star becomes red giant following a track to our upper right hand corner of HR diagram. As you can see, this track. As the core temperature reaches 300 million Kelvin, helium burning starts, which halts the star's cooling and increasing luminosity. Now star moves down and leftward in HR diagram, but when the helium burning in the core stops, the star again moves to right and upward on the diagram following the previous. This red giant track, so they are named as asymptotic giant branch. Usually the stars with low or intermediate mass 6 times or 10 times the mass of Sun in their life in AGB stars. These types of stars are main dust distributor or dust in ISM, obviously because of their high mass loss rate. On the basis of percentage of carbon or oxygen content, AGB star fit into three broad categories: M-type, C-type, and S-type. Next, we have interstellar medium, or basically known as ISM. ISM is the matter and radiation that exists between stellar system. It contains 99% gases, of which 90% is hydrogen, 9% helium, and 1% other gases, and then 1% dust by mass, and also contain cosmic rays and magnetic fields. Talking about IRIS, infrared imaging surveyor, and Akari, meaning light in Japanese. Akari was also known as AstroF or IRIS previously. Akari survey was conducted in 4 wavelength bands at 65, 90, 140, and 160 micrometers. IRIS survey was conducted on a similar band of that IRAS mission, that is 12, 25, 60, and 100 micrometer. IRIS and Akari has much higher sensitivity and better spatial resolution than that of IRAS, so we focused our research on IRIS and Akari survey. So what motivates us to do this research are increasing interest in study of evolution of universe. IRAS and Akari has opened the door for conducting entire research work, and software like Aladdin, Origin, and Excel made it much more easier to work with large data. These are the main objective of research. As you can see here, we intended to study the structure of flux, dust color temperature, and dust mass, to fit Gaussian mass and Gaussian temperature, and to know the model of structure formation. Onto the theory, we have used expression 3 in order to calculate the temperature of cavity in iris. Here R, as you can see, is the ratio of flux densities, and beta is the spectral index. We assume that dust in ISM is crystalline structure, so value of beta equals to 2. Expression 4 is used to calculate the temperature of cavity in Akari map. For calculation of dust mass was reduced, and we actually use expression 7 for calculation. Then we have Planck's function, which helps to measure the intensity of radiation emitted by dust. We use expression 6 to calculate intensity of radiation. Also, for calculation of inclination angle, we use expression 8. Here Q is intrinsic flatness of the structure and it depends on the amount of molecular hydrogen and the dust. The value of Q used here was 0.3. We use Sky Visual Observatory in order to search an isolated cavity for different wavelengths in iris and Akari band for RGB data. Then we perform systematic search in RA 1 hour 17 minutes and declination 63 degree 22 minutes. The coordinate system that we used was Z2000 under gonomic projection. We chose 60 micrometer and 100 micrometer with image size 1 degree by 1 degree in iris map and 90 micrometer, also called as wide S, and 140 micrometer wide L with image size 0.5 degree by 0.5 degree in Akari map. These are the 4 images we have selected. Above images are obtained from iris survey and Akari survey images are below. First map obtained using Aladdin. Calculation of temperature, dust mass, and intensity of radiation was done using Microsoft Excel. Contour, Gaussian, and polynomial plots were done using Origin, version 5 and version 8. We use various methods of drawing contours at different levels. As a result, we can separate the region of maximum and minimum flux regional point. Then by tagging on each pixel bounded by the contour, we get the flux densities in each tagging point. The best contour level has chosen in between different candidates. Here the scatter diagram is shown. This diagram is same as the contour map after the background correction in the region of our interest. There were 267 pixel tag on iris and 1834 on Akari survey. This graph shows the variation of flux in higher wavelength and lower wavelength in both surveys. In iris survey, flux is uniform, but in case of Akari survey, the flux is concentrated on right side of graph. For Gaussian plots of temperature in dust mass, we have used Origin 5. To study about thermal equilibrium, we study Gaussian distribution of dust color temperature. Since the temperature shows good agreement with Gaussian, we can see that our region of interest is in local thermodynamic equilibrium in both surveys. And hydrodynamic equilibrium can be studied through Gaussian distribution of dust mass. In both surveys, most of dust mass are near to average dust mass. We can see that it shows a good agreement with Gaussian. This contour plot shows the distribution of dust color mass in our region of interest in iris survey. A red color represents the higher value and violet for lower. This contour graph shows the inverse relation between dust color temperature and dust mass. The region with higher temperature has lower mass, as volume is constant. And this contour plot are in Akari survey map. The color representation is the same in all contour plots. This graph also shows the inverse relation of dust color temperature and dust mass. This contour are for variation of flux in lower wavelength in both surveys. And this contour plot is for variation of flux in higher wavelength. You can see here the outline of the contour map has higher flux density. This contour plot shows the intensity of radiation emitted by dust. The region with higher temperature has higher intensity of radiation. In addition, we have studied the variation of Planck's function or say intensity of radiation along the major diameter or extension and minor diameter or compression of cavity. In both surveys, B nu T is dependent on the distance in extension and compression. Help the relation between B nu T and distance for all graph fitting in major diameter. This graph is the study of variation of intensity of radiation emitted by dust along compression. In all the study of variation of intensity of radiation, we found that Gaussian fit have comparatively higher regression coefficient. This equation also shows the relation between B nu T and distance for fitting diameter. We have also calculated the size of cavity by using formula L equals to R times theta and found major and minor diameter. Here R is the distance of structure from Earth. For the value of R, we use this paper. As reference, you can see the value of major and minor diameter in the table. These are the main conclusions of our research. By using Aladdin, Excel, and Origin, we are able to investigate the model and physical properties of cavity of our region of interest. The average temperature was found to be 23.49 Kelvin in iris and 16.43 Kelvin in Akari survey. The average dust mass was found to be 3.02 into 10 to the power minus 3 times the mass of Sun in IRIS and 2.35 into 10 to the power minus 2 times the mass of Sun in Akari survey. An inclination angle was found to be 77.6 degree and 84.56 degree for IRIS and Akari survey, respectively. Further research can be conducted on different coordinates, and they can study the impact of stellar wind on mass loss of AGB star. At last, I would like to thank IUST, TU, Department of Physics, Amrit Campus, my supervisor, Mr. Devendra Raj Upadhyay, and Professor Dr. Leela Pradhan Joshi, HOD, Department of Physics, Askal, for giving me this opportunity to do this research. I would also like to thank ANPA, Nepal Physical Society, and Physics Research Initiative for providing such a good platform to present my research. And I am grateful to you all who, amid the chaos of COVID-19 pandemic, have managed your precious time for this. These are the references that we used during this presentation. Thank you.
Thank you, Manish. It's a nice talk. I'm trying to see any questions. What happened to my screen?
So I have one question for.
Yes, please go ahead. Let's start the question.
So basically, like, what value of gas to dust mass ratio you have used?
Is Manish here? That's the first question.
He's not here.
Well, I should have.
Hello? Yes, he is here. He is here.
Okay.
So, can you please repeat the question?
So basically, what value of gas to dust mass ratio you used? Because when you calculate dust mass, you need those ratio, right? So I just wondering, like, what value of gas to dust mass ratio you use to calculate your mass?
So actually we have, in the presentation, we have used expression 7 for calculation of dust mass, and dust mass depends upon the temperature and intensity of radiation.
So the AGV star you're talking about, is it a carbon rich or oxygen rich?
Carbon rich star it was.
All right.
How far is this star?
So we have used a paper as a reference, and we have found that it was 4,990 parsec from Earth.
Okay, that's pretty far. And so your data seems very good. Do you have collaboration at Akari, or did they make these data public so that you can just download it? Like,
So there is Discovery Virtual Observatory website.
Okay.
And first we have downloaded the FITS image. The FITS image gives all the data related to the flux. So after getting the data about the flux, we can reduce it and calculate what we intended to calculate.
How do you read the FITS data?
Flux data by tagging each pixel by background correction and making a good contour.
What software are you using? Do you use PyRef, IREF type things?
We have used Aladdin version 2.5.
Okay. Do you know my tech person here? Do you know how to read text? What happened to my WebEx? It's if there are any in the chat message, I'm trying to see if there are any here it is.
Okay, I don't see any questions on the chat over here for Manish. So yeah, I don't see any questions for in chat.
Yeah, please remind.
So I have one more question for Manish.
Okay, go ahead.
Yes, sir.
Please go ahead.
So basically, like what optical constant did you use to find the absorption efficiency?
We have. I have no idea about the absorption efficiency, sir.
Oh, okay.
Does anyone in the audience have the answer?
Well, I'm also the specialist of AGV stars, so
Okay.
so basically, yeah. So when you do the efficiency, basically you work with the absorption and scattering phenomenon of those interstellar disk, and then you use some optical constant value to find those efficiency. But I was wondering like what kind of the NK data, the optical constant data he used.
Okay, so maybe you can discuss later and
Oh yeah, sure.
yeah, give some insight to Manish these things. Thank you so much.
Thank you, sir.
Um,
Thank you.
so, are there any other? If not, I would like to move on to uh, our next speaker, Meghnad Upadhyay, Tribhuvan University. Uh, let me. He's going to talk about formulating a methodology to calculate. Meghnad, are you there? If not, please stand by for the question session at the end of the talk. So here is Meghnad Upadhyay.
Good afternoon to you all. Let's introduce myself. I am Meghnad Upadhyay, a regular MSc student of Water Mathematics. Today, I am going to present on topic formulating a methodology. Now I would like to enter.
Sorry about that. I think it's my fault.
Good afternoon to you all. Let's introduce myself. I am Meghnad Upadhyay, a regular MSc student of Water Multiple Campus. Today, I am going to present on topic formulating a methodology to calculate local sunrise sunset time in Nepal. Before entering on my topic, I would like to express my deep gratitude to my thesis supervisor, Professor Dr. Narayana Prasad Chapagai, TU, Dr. Suman Satyal, UT Arlington, USA, Dr. Sri Krishna Bhattrai, UNCC Charlotte, USA, for their valuable time and consideration. Now I would like to enter on my topic. Let's move on introduction section. In the context of Nepal, we are calculating the sunrise, sunset, and twilight time through the ephemeris of Royal Meteorological Society. We do not have our ephemeris to calculate sunrise and sunset time. We are using Indian, American, and British ephemeris. Mostly, we are using Indian ephemeris. By practicing such method, the sunrise and sunset time can't be matched exactly in Nepal due to the variation in latitude, longitude, altitude, etc. The purpose of my study is to calculate this time and compare it with data published by Nepal Panchanga Samiti and also with observational. Let us move on celestial dynamics section used on my study. First celestial dynamics used on my study is solar elevation angle. Solar elevation angle is the angular height of the sun in the sky. Solar elevation angle is also a altitude angle. While analyzing the graph, solar elevation angle decreases with increasing geometrical height. Negative sign in the formula indicate inverse relation between geometrical height and elevation angle. Let's move on second celestial dynamics, that is time of meridian passage. Time of meridian passage is an instant of time at which sun is directly overhead of us. At this time, sun's rays are directly perpendicular to given line of longitude. Time of meridian passage is also called solar noon. Small d used in the formula indicate fraction of the day, and capital N used in the formula indicate number of days in a. For example, N is equal to 1 for January 1, N is equal to 31 for January 31, and N is equal to 32 for February 1. Let me elaborate further on third celestial dynamics, that is solar hour angle. Solar hour angle H is the angle that represents the position of sun with respect to clock hour and with reference to sun's position at 12 noon. At the time of sunrise and sunset, the value of solar elevation angle is taken as 0. So we got the required expression of solar hour angle. Phi and d used in this formula indicate the latitude and declination angle. Let's move on fourth celestial dynamics, that is solar declination angle. Solar declination angle is the angle made by the line joining the center of sun and earth with its projection on Earth's equatorial plane, as in figure 6. Solar declination angle varies seasonally due to the tiltation of Earth on its axis of rotation. N E used in the formula indicate the number of days in a year. Let us discuss phenomena of analemma formation. An analemma is the diagram that can be obtained by plotting the azimuth and solar elevation angle. Analemma shows the position of sun in the sky. North-south component of analemma shows the sun's declination. While discussing on causes of analemma formation, we get the two types. That means first elliptical orbit effect and next effect due to tiltation of Earth. Now I want to discuss on sunrise and sunset times. Sunrise and sunset time can be understood from the sun's position relative to horizon. From the figure 9, it can be understood that sunrise occurs when the upper edge of the sun rises just above the horizon. Sunset occurs when the upper edge of the sun sinks just under the horizon. L, M, and H used in the formula indicate the longitude, time of meridian passage, and solar hour angle, respectively. Now, I would like to move on result section. Based on my finding, drawing graph has been obtained by using the parameter mentioned above in figure. First graph is of sunrise time. While analyzing the graph of figure 10, earliest sunrise of the year has been found to be in the month of June, and latest sunrise of the year has been found to be in the month of December. Next graph is of sunset, as in figure 11. By analyzing the figure 11, it has seen that earliest sunset of the year has been found at the month of December, and latest sunset of the year has been found at the month of June. By observing above two graphs, longest and shortest day of the year has been found to be June 21st and December 21st, respectively. Third graph is of declination angle. Declination angle has found minimum at winter solstice, that is December 21st, and declination angle has been found 0 at March 22 and September 22, and its value maximum at summer solstice, that is June 21st. While analyzing the variation of our angle throughout the year, longest day of the year has found to be June 21st, and shortest day of the year has found to be December 21st. In conclusion section, let me sum up my main points. Calculated sunrise time seems to be earlier when compared with calendar-based sunrise time, and calculated sunset time seems to be later when compared with calendar-based sunset time. Due to the effect of atmospheric refraction, position of the sun gets shifted, so variation seen in calendar-based and calculated sun hour. Longest and shortest day of the year has been matched with calendar-based data. Soon, I would like to work more in this topic along with my friend to obtain more accurate result to minimize the possible error. I would like to thank my thesis supervisor, Professor Dr. Narayana Prasad Sapagai, TU, Dr. Suman Satyal, UT, Arlington, USA, Dr. Sri Krishna Bhattarai, UNCC, Charlotte, USA. Also, I would like to remember my colleagues who support me directly and indirectly for this study. These are the references used on my study. Lastly, thank you for your attention. Now,
Okay, so so I see one question in the text, in the chat here. Meghna Chalise, Upadhyay, are you there?
so only Meghnath is there.
Okay. So I believe this is the question from Bhupal Katel. Angles. Like what methodology did you use to calculate those angles? I believe the solar angle.
That means we are using the
Yeah, I think we have bad connection with Meghna. It's breaking up.
especially we are using
Okay. I still have a minute. If anyone has any questions.
Excuse me, sir. Can I ask a question? Excuse me, sir.
Yes, please go ahead.
I would like to, first of all, I'd like to thank for the presenter for the lovely talk. And I'd like to ask about the analemma. I'm pretty much interested in this term. I'd like to ask, is the analemma for the sun, have different shapes on different planets, or the analemma of the sun is the same for all the 8 planets? Or in which kind of factors does the analemma depend in various planets?
Okay, sir. Thank you for the question. Especially we are observing the sun observing from angle, and while discussing the factor depending on sun, latitude and longitude used and by using solar elevation angle, that solar elevation angle, that means altitude and azimuth, then your that type of shape.
So if I look the analemma of the sun from a different planet, for example, from a Jupiter or from Mars, does it have the same 8 like in Earth, or the shape of analemma changes when we go to when we observe the sun from the different planets?
Okay, sir, we are doing this from that limited specific location that more location is I also don't know, sir.
Okay, thank you, sir.
I want to add quick on that. Yes, this analemma is very location specific. So even within Nepal, if you're recording it, if you're plotting it for different latitude and longitude, you'll get a different shape, and you would see different shape from Europe, Asia, America, and so on. And this is, I'm glad you're interested in it. We're looking for some volunteers from Nepal who can actually get the observation of for this type of shape, meaning basically taking pictures of the sun. It doesn't have to be every day. You can do every week. If it's somewhere around a historical location, that's even better. Take a picture of the sun every day, but it has to be, the camera has to be at certain height throughout the year. And then if you superimpose all those images together, you'd get these type of 8 shape, some that go beyond the horizon, and uh, the negative latitude and so on. But again, if you are interested, you can contact Meghnad GP or me later. For now, I'd like to move on to next talk. Again, thank you, Amrit. Is Dravindra here? I hope he will join as if he's not already here. So here is Dravindra's presentation for today.
Good morning, good afternoon, good evening to all present in this meeting. It is me, Ravindra Pandit. Today I am going to present my research on title Analysis on North-South Component of Geomagnetic Field with Interplanetary Magnetic Field during intense geomagnetic storms of 22nd June 2015 and 25th August 2018. Now these are the outlines of my presentation. Now introduction. Geomagnetic storms begin from sun. Sun appears as a constant glowing star when it seems as a naked eye, but when it seems as a when it has been found that it has different rate of emission and it has 4 phases. that phases repeated after 11 years called solar cycle. The phases are minimum, maximum, ascending and descending. During maximum phases it has no emission of the particles, ionized particles, and during the minimum it has less emission, and sun emits a continuous plasma that is called solar wind. When the solar winds move towards the earth, it bombards on the earth's magnetosphere, and magnetosphere get compressed on the day side, elongated on the night side. And the solar wind has ionized particles, and those ionized particles has frozen magnetic field called interplanetary magnetic field. When the interplanetary magnetic fields are resolved in three different directions, one of them is called Bx component, which is directed towards the sun. Other is called By, which is directed towards the east, and the other is Bz component, which is directed towards the north and south. And this picture shows that geomagnetic reconnection between the magnetic fields of the interplanetary magnetic field of the Bz component and the magnetic field of the geomagnet. And red regions show that there is a reconnection the night side and the day side, and the left region show that day side, and right picture show red that night side. Now, when there is reconnection, the magnetic field of the Earth get balanced, cancelled by the interplanetary magnetic field. As a result of that, the plasma enters into the Earth's magnetosphere and produces destruction in the magnetosphere, ionosphere, as well as the system into the space and on the Earth. Now, when the ionized particles enters into the Earth's magnetosphere, as a result of the geomagnetic field, it gets trapped and begin to move in a particular radius, construct a current called ring current, and this ring current reduces the magnetic field of the Earth. Now, this shows that the list of the geomagnetic stations used in our study. We have selected the geomagnetic station located at equator and mid latitude and high latitude region, and these are the distribution of geomagnetic stations on the global map, and this shows that most of the magnetic stations taken in our study lie in the northern hemisphere. Now, result and discussion. Now, this shows that variation in geomagnetic indices due to the storms of 22nd June 2015. Now, the plot in from top to bottom in the first panel shows that variation in total component of magnetic field. The second represent the X component of the magnetic field. Other is Y, and the Z component of the geomagnetic field. Magnetic field, and the down panel shows that variation in image. Now, this shows that variation in geomagnetic indices due to the storms of 25th August 2018. And the panels from top to bottom shows that total magnetic interplanetary magnetic field, X component, Y component, Z component of the interplanetary magnetic field, the image of the measured on the Earth's surface. Now, these show that variation in X component of the magnetic stations at measured the magnetic stations that are located at equatorial region. The stations are abbreviated by API, GUA, KOU, MPO. Now, this shows that variation in X component at the same stations, but due to the storms of 25th August 2018. This shows that variation in X component has more on the 25th August. Now, We show that variation in X component at mid latitude station, the storms of 22nd June 2015. Now in this panel, it shows that variation in the at the these stations had higher value on the 22nd June. Now this shows that variation on the same station but due to the storm for 25th August 2018. Now this shows variation in the magnetic stations located at the high latitude due to the storm for 22nd June. And this shows the magnitude varies at different stations. Now this shows that variation in X component or the high latitude because of the storm for 25th August 2018. Now this shows that variation in X component continuous wavelet transform at Alibag stations. The storms of 22nd June 2015. Now in power spectrum plot, the red intense region represents the region where the geomagnetic has taken place. And in this plot shows that variation in X component using the continuous wavelet transform again at the Alibag station, but due to the storm for 25th August 2018. This shows that the magnetic storms taken place in the early morning. Now we have studied the correlation between BH, BY, and BZ component with X component of geomagnetic stations located at different places across the globe. And this shows that correlation between the XYZ component with X component at Galibag station due to the storms of 22nd June. Now this shows that variation in correlation chain and correlation scatter plot with the Galibag stations due to the storms of 25th August 2018. Conclusion. The X component of geomagnetic field is affected by the geomagnetic storm. The effect vary with latitude and longitude. Maximum effect is observed at the station located high latitude. Correlation between X, Y, Z component of magnetic field with X component has no specific order. Variation in X component may depend upon types of magnetic ground conducting station, wide current, and disturbance from lower atmospheric phenomena. That the references I would like to express sincere thanks to the supervisor, and the professor and the Ronald, the Department of Physics, the Central Department of Physics, and Department of Physics, and the campus staff for providing fellowship. Thank you. Question, please.
Yes. Do I have any question here?
Ravindra Pandit. Today I am going to present my research.
So, Dravindra, are you there?
Yes, please, sir. I'm here.
Okay. Yeah, there were. No, it was your question that you can hardly hear. Okay, so if you have any questions, please unmute your mic and ask Davindra a question. Meanwhile, I'd like to start with one question. So all these, geomagnetic stations, can you contact them and, gather this data, or do we have one in Nepal?
No, sir. The data are available on online, so we have downloaded the data from the websites and did the calculations for the results.
Okay, that's general. One physics question. So I guess the eventual goal of studying the geomagnetic storm is to predict the sun weather, if I'm not wrong. So you're trying to predict how sun behaves, right? And if we can predict beforehand when sun, sends out these flares, and um, see if we can, uh, uh, know beforehand if we are getting some high charged particles, headed to the Earth. Is that right?
Yes, yes, sir. Yeah, basically studies, these all studies about the study of the space weather, with a particular study with these two storms.
When was the recent this geomagnetic storm? The recent one was in 25 August 2018, or maybe after that?
No, there are so many geomagnetic storms, but we have studied about the intense geomagnetic storm. Some of them are very weak, some of them are intermediate value storms, some of them are very, very severe storms. So we did we did only these two storms, study of these two storms. There are storms coming, but the nature of the storm depends upon the phases of the solar cycle, whether the sun is in the maximum phases, minimum phases, or what kind of phases. It has four phases. If the sun is at the maximum phases, then maximum intense geomagnetic storms are emitted. When it is in the minimum phases, at that time, minimum intense geomagnetic storms are occurred on the Earth's surface.
Okay. One last. So when was the recent, biggest storm that happened on record?
uh, this solar cycle is of 24 solar cycle. So in this 24 solar cycle, this is the 25th August 2018 is the biggest, I think.
Great. Thank you, Ravindra, for this talk. Uh, and I would like to move on to our next speaker, uh, mm, Ganga Prasad Adhikari.
Respected Professor, my dear friends, I am Ganga Prasad Adhikari, MSc student from the university. I am going to present my project work calculating solar and sunset time for wide aware of Nepal. Introduction. From the scientific calculation of solar and sunset time for Nepal motivates me to work on this project. Currently, Nepal is calculating sunrise and sunset time from British and American informations. And Nepal continuously also releases a sunrise and sunset time, but the method of calculation is top secret. They are clicked into calculation method here. Our goal is to build the formula and present models and to calculate the local mean. And we will share this information with all with the method of calculation. This is not secret. Here we see celestial sphere, equinox, celestial equator, and elliptical orbits. In celestial dynamics, we discuss about declination angle, solar altitude, and hour angle. Declination angle for sun can be determined by this formula, and the value of the sun declination angle rises throughout the year. It is maximum June 20 until 2.5 degree, June 0 equinox, and again 0.5 degree on December 22. The variation of the declination angle can be seen. Altitude is denoted by the alpha, and it is the position of the sun rising. Value of the altitude can be from this formula, and the azimuth also can be calculated from the given formula. And here delta is declination angle, phi is altitude, and capital S is hour angle. Hour angle is the angle between the star meridian and observer meridian. Sunset and sunrise time, we can calculate hour angle by setting alpha equal to 0 in the question of previous slide. On considering the reflection effect, the hour angle modified, and we will have to consider the shift of the position of the sun due to the atmospheric effect, which is 0.83 degree. Time correction for any longitude, we have to consider time correction because there is a difference between the LSTM and the longitude. LSTM is the value of the local standard meridian time, which can be calculated. Which can be calculated by using the delta T. Delta T is the difference between GMT and the local time. For Nepal, it is EOT is the equation of time, which we use in time correction also. And the difference between the solar time and solar time is calculated. What obligatory and what forward essentially causes the difference between solar time and solar time. We will discuss these two causes separately. And effect of the orbital stability. Under this effect, we will consider the Earth as the perfect circular orbit, but has oblique and due to this effect, there is also differences in solar time to solar time. We can calculate the combined effect of the because by combining these two effects, and then the combined effect can be seen by another is the position of the sun. When we view the sun from fixed point and fixed time over the year, and we have plotted the figure of the NLM for variable volumes for the 1 day. You can see the graph. And sunrise and sunset time, sunrise and sunset time can be found can be calculated from these two equations, when TC is time correction and F is angle, and time correction can be from this equation, which we already discussed. So we see the variation of declination throughout the year, and it becomes maximum on June and December, and 0 at excess equals present. Similar like a frame, we observe in the hour angle as well. So hour angle also becomes maximum on June. Our main goal is to determine the sunrise result. What and the calculated value is represented by the red line. Red line and calendar baseline is calendar baseline is represented by the blue line. There is a difference between these two lines, which can be the effect of atmospheric refraction and altitude of location. And we can see that from the figure we can see the maximum or longest daylight time is occur on June month. And we have calculated this data for wherever and once you can achieve previous sections, we have seen that from the field of NMR, the solar age is maximum 77 degrees and azimuth is 165 degrees. The solar azimuth or NMR position of the part of the sun is tracked with 67 degree altitude and 142 degree azimuth. The value of the hour angle is maximum or the point of azimuth. The variation of the calendar date and the calculated data was thought to be about 15 minutes, and the difference can be the effect of the atmospheric reflection on altitude. And we still, so far not sure which one of which graph is correct, so we need some special verification, and for this we will take 10 or more different measurement for the sun dimension system in the clear sky. So the average of these data will give the accurate or nearly equal value for the sun dimension system time. This is our future work for this project. And I'd like to thank my supervisor and my colleagues. These are my references. Thank you, and feel free to ask questions.
Okay. Thank you, GP Adhikari. Yes, first I would like to apologize for the sound quality there. We did not verify it in the beginning, and but I think GP did a great job, though the sound was low. Yes, thank you, Prakash Pandey. That's a very nice suggestion. We'll definitely consider it. Are there any other questions? Are we doing okay on the presentation, sharing screen, the technical wise?
Yes, Suman sir, we are good. Yeah, except the sound quality for this recent presentation was not that great, but that I think it's okay.
Great. Again, thank you all for your cooperation and understanding. I'd like to move on to our next presenter, Janak Ratna Malla. So Janak is a PhD scholar at Central Department of Physics, Tribhuvan University. Today is going to talk on spatial orientations of angular momentum vectors of galaxies in supercluster S 24704000029 and substructures. I'd definitely like to know what these numbers stand for. So let's start with Janak.
First of all, I would like to thank ANPA NPS for organizing this program. Today I am going to present my presentation on topic spatial orientation of angular momentum vectors of galaxies in supercluster S247 plus 040 plus 0029 and substructure. I am Janak Ratnamalla doing PhD under supervision of Professor Dr. Binir Aryal, Head, Central Department of Physics, Tribhuvan University, Kirtipur, Kathmandu, Nepal, and co-supervision of Professor Dr. Walter Sauer, Institute of Astroparticle Physics, Innsbruck University, Austria. Contents of talks are introduction, methodology, result and discussion, conclusion, references, acknowledgement. Now, introduction. A galaxy is a gravitationally bound system of stars, stellar remains, interstellar gases, and dark matter. Galaxies range in size from few billion to 100 trillion stars. Galaxies are categorized according to their visual morphology as elliptical, spiral, and irregular. Many galaxies are thought to have black holes at their active centers. A galaxy cluster is a structure that consists of anywhere from hundreds to thousands of galaxies that is bound together by gravity with typical masses ranging from 10 to the power 12 to 10 to the power 14 solar masses. Superclusters are large group of smaller galaxy groups and are among the largest known structures of the cosmos. There are three galaxy evolution models. They are turbulence model, pancake model, hierarchy model. Turbulence model. This model proposed by Ozorn in 1978. In this model, spin vector of galaxies are perpendicular. In this model, first flattened, rotating protoclusters overform due to cosmic vorticity in the early universe. Turbulence model pancake model. This model, proposed by Doroskip and Centurin 1978. In this model, spin vectors of galaxies are parallel. In this model, clusters were first formed and they fragmented into galaxies. Here, adiabatic fluctuation takes place. Hierarchy model. This model proposed by Peebles 1969. In this model, spin vector galaxies or first formed and then obtained their angular momentum by tidal forces while they were gathering gravitationally to form a cluster with no dissipation. Now I'm talking about methodology. Here we have to find inclination angle by using Hollenberg equation, that is cos square I equals to b square by a square minus q star square whole divided by 1 minus I is inclination angle, b by a is axial ratio, q star is intrinsic flatness whose value is 0.2 for oblate spheroid. Headman et al. 1972. In the figure, we can see that there are two positions, fashion and agent. In case of fashion, I equals to 0 degree and agent, I equals to 90 degree. In Gorlowski transformation, we use the method proposed by Flynn and Gorlowski 1986 in order to convert two-dimensional data to three-dimensional galaxy rotation axis. We have to find polar and azimuthal angle. We have to need four parameters that are right ascension, declination, position angle, and inclination angle. Inclination angle we have to find by using Hollenberg formula, and other are the data provided by collaborator Institute of Astroparticle Physics, Innerforce University. Now I am talking about in the figure the all-sky distribution of galaxies, which indicates the inhomogeneous distribution of galaxies. We can see that almost all the galaxies are found to be grouped in the different region of space of supercluster. So the small group are I circled with red color that are substructure. Here 1331 number of galaxies, which is shown in density of galaxies. In addition to statistical tests, we also study Holmes and dips in polar and azimuthal angle distribution. In polar angle distribution of the supercluster, as shown in figure, we can see that up to 45 degree, the small increased value in observed data give the significant humps. This hump signifies that the spin vector orientation of galaxies tend to orient parallel with respect to the equatorial coordinate system, and by bimodal region, no significant hump and dip. After bimodal region, that is 5 degree, there is hump at theta equals to 55 degree. This hump is due to 13 more observed solutions than expected solution. These suggesting strong isotropy in polar angle distribution. In azimuthal angle distribution of supercluster, there are two small dips in the plot at phi equals to minus 75 degree and at 55 degree, but they are insignificant and they are due to difference in number of observations than that of expected. So we can conclude that there is no preferred alignment of spin vector of galaxy. This suggesting strong isotropy in azimuthal angle distribution support hierarchy model. In this plot, statistics of polar and azimuthal angle of supercluster. For polar angle, the value of is 0.511. Autocorrelation coefficient is minus 0.747. First order Fourier coefficient is minus 0.180. First order Fourier probability is 0.954. Here all statistics show the isotopic distribution of spin vector in the supercluster support hierarchy model. In azimuthal angle distribution, the value of chi-square probability is 0.950. Autocorrelation coefficient is minus 2.206. First order Fourier coefficient is 0.401. First order Fourier probability is 0.633. Here all statistical test shows strong isotopic distribution of spin vectors, supports hierarchy model as proposed by Peeble 1969. Similarly, we can explain substructure due to time constraint. I directly move to conclusion. My main conclusion of the talk is we have to calculate statistics of supercluster and their 5 substructures. Our result found isotropy supporting hierarchy model as proposed by Peeble 1969 of galaxy evolution. Here are references. Acknowledgement. I would like to thank Professor Dr. Bill Aryan, head CDB2 supervisor. Thanks.
Okay, thank you, Janak Malla. See. I don't see any questions in the chat room. I don't have any questions either. This seems like a very complicated topic for me.
So what was the correlation coefficient value, in your slide?
Okay, Janak, are you there? I'm sorry, I think we lost the speaker.
Oh, that's fine.
Again, sorry about that.
Nepal राति छ त्यो
probably you'll have connection. Okay, so I would like to move on to our next speaker. Next speaker is very familiar to me. Devraj Joshi from University of Wisconsin. He did his PhD from Boston College. We go back 20 years, right, Dave? We started our physics career together 20 years ago in Nobel Academy in Bhaneswar. Again, it's good to see you now.
That makes me nostalgic.
Yes. So let's hear from Dave about the influence of the background ionospheric density on the irregularity parameter characterizing the equatorial ionospheric irregularities.
So it's a recorded presentation. I'm afraid like it might not be as good as if I would have talked live. Okay. So with that apology, like please go ahead, Suman. Thank you so much for
it's all right. And I'm sure you'll hang around for any questions later. So, or if you think if anything is missed, you can always add on after the presentation.
Yeah. Hello, I'm Dev Joshi. I'm currently a postdoctoral research associate at the University of Wisconsin, Pennsylvania, USA. Today I'm talking on the influence of the background ionospheric density on the irregularity parameter characterizing the equatorial ionospheric irregularities. This is the work done by me under the supervision of my PhD advisor, Dr. Keith Groves, while I was working as graduate student and briefly as research associate at Institute for Scientific Research, Boston College, Massachusetts. Before I proceed, I would like to acknowledge Dr. John Ritter at ISRBC and Dr. Chao Song Hong and Dr. Patrick Roddy at AFRL, Albuquerque, New Mexico for many useful suggestions, discussions, and comments through this work. With a very brief introduction on the ionosphere. Ionosphere, according to one definition, is the battleground between the Earth's neutral atmosphere and the Sun's fully charged atmosphere in which the Earth is embedded. The incoming solar radiation ionizes the constituents of the Earth's neutral atmosphere, leading to the creation of stratified plasma layers. In the image in the left, we see nighttime and daytime profiles of the ionosphere, which show these stratified plasma layers. The daytime profile has higher plasma density because of the region that the ionization occurs during the day. These stratified plasma layers reflect, refract, scatter radio waves depending on frequency, density, and gradients. One of the very common instability in these layers is Rayleigh-Taylor instability, which occurs during day and to night transition. Other instabilities also exist in regions of large gradients and strong flows. When radio waves traverse through these instabilities, it leads to highly variable reflection and refraction called as scintillation, which motivates our work. That motivates our work to understand these equatorial ionospheric irregularities. Our main goal is to understand the spatial distribution of equatorial ionospheric irregularities as a function of solar flux. These irregularities are associated with, as I said earlier, intense radio wave scintillations that impact space-based navigation, communication, and remote sensing systems. While models of occurrence frequency exist, the extent of the regions affected is poorly understood, and the validity of physics-based models of the underlying instability. Let's take a look at the data itself. In the image in the left, I'm showing a day of observations made by planar Langmuir probe sensors on board CNOP satellite. In the right, I saw two instances of zoomed in portions of this data. In the upper subplot, we see the density is rapidly varying. In the lower subplot, we see the ion density is not rapidly varying. It is in fact smoothly changing. So we we are interested in the instances of the upper subplot, which we are calling equatorial ionospheric irregularities. These are important because these impact radio waves traversing through these regions. Characterize these ionospheric irregularities, we define an irregularity parameter as shown in the mathematical equation here. The equation represents the standard deviation and ion density of ion density variations in logarithmic scale divided by the mean of ion density in logarithmic scale. We see in the plot, the blue curve represents ion density, the red curve represents the irregularity parameter. Whenever the ion density is changing rapidly, the irregularity parameter has higher values. After careful observations and comparisons with previous studies, we choose sigma, the irregularity parameter, to be 1.2 as the criterion to capture an instance of irregularity in the observations. With that definition of irregularity, we construct climatological plots to understand the features of the occurrence percentage of these irregularities. Our climatological features are consistent with previous studies, where the occurrence probability is generally high in equinoctial months and low around June solstice, and it maximizes in the longitude sector from 280 degrees east to 20 degrees east. As we go higher, the peak percentage decreases in apex altitude, as we see in the images. But we are interested in the peak heights of these irregularities. They attain at the magnetic equator. That is important because the height at the magnetic equator determines the original extent of these irregularities. We develop a scheme to decipher peak heights from the observed heights of these irregularities. After carefully analyzing the scheme, we process the data to understand the variation of the peak height distribution of these irregularities with solar activity. The peak apex height distributions of the irregularities vary with solar activity as seen in the median of the peak apex height distributions of the irregularities rise from about 491 km at solar minimum to 737 km during solar maximum. The tail of the distributions rises more rapidly with solar activity as seen in the 90th percentile scatter plot and the line fit. The model results taken from the physics-based model PBMOD also fit the observed results very well. Now we take a step back and ask another question. If the irregularity parameter we are using to characterize the irregularities is indeed the right parameter, we want to specifically ask if the parameter sigma is being influenced by the background density. The question is motivated by the scatter plots we are seeing here. In the scatter plot, sigma is decreasing with increasing altitude, and with increasing altitude, we know the background density of the ionosphere decreases. Hence, we wanted to understand if the parameter is being influenced by the background density. We look at sigma, we look at the deviation of the ion density in linear background density. We see with physical altitude, all of them seem to be decreasing. And we plot quartile plots out of those distributions, and the 25th percentile plot has decreased by 20% for sigma. The decrease is not as rapid as seen in the scatter plot, but we wanted to understand if 20% is significant enough to be called as being influenced by the background density. We now look at the data in a different way. We bin the observations in physical altitude and see how they vary in apex altitude. We see sigma values closer to the magnetic equator at lower physical altitudes are higher than those farther from the magnetic equator, which is not the case with the irregularity parameter defined in terms of linear scale. So it requires more investigation to understand the influence of background density on the irregularity indefinite conclusions. Now I'll present the conclusions of my work. The CNOS bubble occurrence statistics are consistent with previous work related to this topic. The numerical simulation demonstrates that CNOS absorbs less than half the irregularities during high solar activity years and about 1/4 during low solar activity years. The analysis indicates that the median height distribution of bubbles increases linearly from about 491 km at solar minimum to 737 km during solar maximum. These results apply to the -80° west to 10° east longitude sector. In the PV mod model, the field line integrated connectivity is found to be the key determinant of terminal bubble altitude. More investigation is required to reach towards unambiguous conclusions on the influence of background density on the irregularity parameter characterizing the ionospheric irregularities. Thank you.
Thank you, Dave.
Thank you so much. Do I have any questions?
And I have one.
Yes, please.
So basically, I understand that, everything is depend on your, electron density.
Yes.
But I was wondering, like, is there any interaction of radio wave with the positive ions? I mean, I know it has a minimal effect, but remember when you increase irregularity, right? So in that situation, your positive ion also increases based on in their density. So I was wondering if there is any interaction of radio wave with the positive ions.
Okay, I think there should be. I have not specifically checked the question, but if we think through it, it's just interaction of radio wave with any media, right? Like, and there should be either it should be positively charged or negatively charged. Either way, there should be.
Yeah, I know it has a very minimal effect because of its large in size, so radio doesn't interact a lot. But my part was when you increase the electron density, those positive charge ion also increases, right? Because you are breaking the electron from those particles. So basically, I thought that there might be some kind of error analysis in your research where you can show that okay, some part of these radio wave should be attenuated by the positive ion as well.
I would think so, but I don't have a very definite answer on this because I have not looked into it. Okay? So, but my first hunch would be yes, there should be some interaction, but the level of interaction and the details I have to check.
All right.
Yeah, I think, now you're here. I think I missed in the talk. Can you give like summarize on what causes this irregularity?
So these are like hydrodynamic instabilities. These are stratified plasma layers. We can imagine them as like a low density, high density fluid being stacked atop low density fluid. Remember, like if we can have a glass of water, that glass, and we can hold it upside down, and a paper can be stuck, right? Or paper can be stuck on a glass of oppositely hold glass of water.
Right.
But a slight similar kind of unstable equilibrium, where low density plasma is where a high density plasma fluid is stacked at a low density plasma fluid, and a slight disturbance beneath the surface can create this low density plasma fluid to move through the high density plasma fluid, which are called plumes, irregularities, spread F. They are given variety of names, and there are very nuances on the differences of those names. But essentially, fluids of changing density are created primarily due to solar radiation, and these fluids can move up and down, creating a change in the previous configuration, and that impacts the communication system because radio waves should traverse through these let us say plumes or fluids of changing plasma density.
Okay.
So what caused the, like the different density in these electron?
That's because of the That's because of the composition of the neutral atmosphere. Let us say initially there was no ionization. Initially there is a neutral atmosphere, and the neutral atmosphere does not have similar composition, exact same composition at all the heights. That's because of gravity. Because heavier ions or heavier constituents of the atmosphere are attracted towards the Earth, right? The lighter ones are above, and the heavier ones are below, and that creates a gradient in the composition of the neutral atmosphere. And also, there is a there is there is it is important. The solar radiation is also not uniform. Not all solar radiation will uniformly penetrate the neutral atmosphere. So it's a combination of those two factors: uh, changing composition of the neutral atmosphere and changing strength of the incoming solar radiation, which ionizes these constituents non-uniformly.
Yeah, that's correct. But aren't we talking about the electron density?
Yes, the electron densities are created out of these neutral constituents that I talked about. Because electron density come out of their parent neutral molecules. Incoming solar radiation hits a neutral molecule or atom, and it frees up electrons and it gets ionized. And these neutral molecules or atoms are not uniformly distributed through changing height in the atmosphere because of the gravity.
All right, thank you.
Thank you so much.
Thank you so much, Dave, and good luck on your
Thank you so much.
rest of your postdoc.
I have one question.
Okay, sure,
Please.
go ahead.
Yes. I would like to ask presenter, what is the basic difference between studying the equatorial anomaly using total electron content and that simply electron density? What would be the basic difference?
Total electron content, and what's the other quantity?
Electron density, simply electron density. In your study, you have studied using electron density, no?
Yeah, total electron content is the measure of the total electron along a path. Okay, so that's an integrative quantity which takes the density of the electrons into account. This simply electron density, we are not integrating it. Okay, so I have not used TEC in my research so far. I just hear that quantity a lot because that's widely used. That's one measure of understanding the disturbances in the ionosphere. One very important and widely used measure. Okay, and this is another measure, and this does not look at the disturbance in an integrative way. Okay, but TEC, total electron content, is by definition an integrative quantity. It integrates the total number of electrons along a path. That's the name. The name itself is revealing total electron content. So what exactly will be the difference? That can be a research question which can be pursued or might have been pursued. I need to check.
Can I ask you?
Or even if it has been pursued, like it will be good to pursue again. Okay.
What would be the basic difference in result outcome using total electron content study of the same phenomena and using electron density?
I don't know. I have not done it. I don't know. And I'm not checked if others have done it. Like, okay. I think we have to start. Yeah.
Sounds like a good thesis topic for someone interested.
Yeah. Yeah.
So can I ask the last one, and then I'm done.
Okay, sure. Go ahead.
So basically, when looking at your, graphing, I saw that, the irregularity was maximum at 10 degree, right? So what factor, is causing those, especially at 10 degree?
Thank you. That's a good question. I think that's alignment of magnetic field with terminator. Okay. There is a hypothesis, Punona's hypothesis, So that's due to the magnetic field structure. Alignment of, okay, that's alignment of magnetic field with terminator. I think that causes maximum upward drift. There is an equation like growth equation, which defines this hydrodynamic instability. The instability we are looking at in particular is relational instability. And one of the very important factor in that equation is the upward drift. Higher the upward drift, the maximum the growth rate, maximum the instabilities. And I think that occurs when the angle between the terminator and the magnetic field is zero, when they align. And there is a, there should have been an image, like if, I think I don't have it here. Yeah. So I might have. So like in DMSP, research is conducted by another satellite in which they try to test that hypothesis, and that is largely proven. There are gaps in that, but that's largely proven. So it's the angle between solar terminator and the magnetic field which leads to the maximum value of a term governing the term in an equation which governs the instability. That's how I'll put it.
Okay.
It's called Sunoda's hypothesis.
Thank you.
That has been widely established, but like any research question, not everywhere. Okay, and people keep pursuing why that does not apply everywhere, but that applies to most of the places. Okay? And I've discussed that in my dissertation as well. Where it does not apply and what could be the possible reasons, and that is discussed widely in the literature.
Okay, thank you again, Dave.
Thank you so much.
Yes, so I would like to move on to our last speaker for this session.
Suman, I would like to steal a minute. This is Sri. Our AGM starts at 2 p.m. So this is the last one, and after this one is complete, the link for AGM has been emailed to all the members. So please check your email. It's a separate link.
What's AGM?
Annual general meeting. You should have got an email like today morning around 10 a.m. about that. Click on and join that meeting, but that link will open only after this session is done because we have got both our WebEx busy. So once this is done, the other link will be active. Thank you.
Okay. So where am I? Here. Okay.
I don't know.
Movie. So now I have Dave R. Sadola from Department of Physics, Western Michigan University. Is going to talk about time-dependent photoionization in Aegean warm observers. Okay.
Hello everyone. I'm going to present my ongoing work on the topic time-dependent photoionization in Aegean warm observer. This is me, Dev Sadola from Department of Physics, Western Michigan University. Currently, I'm doing PhD in astrophysics under the supervision of Professor Manuel Bautista. Dr. Tim Coleman from NASA Goddard Space Flight Center is one of the big. Here is the outline of the presentation. I will briefly explain about what is active galactic nuclei in short Aegean and about warm observer at first. Then I will talk about the necessity of time-dependent calculations. At last, I will give the summary of the whole presentation. Okay, let's start. The image on the right is Seyfert galaxy, where you can see very bright center. Every galaxy is supposed to have supermassive black hole of millions to billions of solar masses at its center. This black hole accretes the ambient materials. The gravitational energy of this accreting matter is then converted into the mechanical and electromagnetic energy. This results the center of Aegean to be highly luminous with order of 12 to 14 solar luminosity. As nothing can escape beyond the event horizon, only way to study the black hole and its time evolution is investigating the matter in the Asian environment. In this slide, the blue line on the left image is the broadband electromagnetic spectrum emitted by the central part of AGN, while purple line represents the blackbody spectrum of stars. We can clearly see that the star emits most of the radiation in visible range, while AGN emits continuum spectrum of about the same intensity from radio to all the way to X-rays. The right image shows different components of active galactic nuclei. In AGN, there are two types of distinct outflow. One is collimated, another is dispersed outflow. In this image, the white cone-shaped structure is dispersed outflow. This gas absorbs the radiation coming out from the central part and produces a lot of absorption lines and edges. The gases which absorbs the X-rays are named as worm observer. Absorption spectra are blue-shifted with few hundreds to sometimes thousands of kilometers per second, indicating gas is moving away from the center. In this slide, I tried to show the typical absorption spectrum of worm observer. We can see so many absorption lines and edges in AGN spectrum. For this, we need high energy resolution. This is one of the absorption feature in the wavelength 15.01 angstrom found in one of the iron ion. If the gas is at rest, it would absorb exactly at 15.01 angstrom, but it absorbs at shorter wavelength. This is purely a Doppler effect. In the above graph, it is moving with about 350 km per second away from the center. Okay, now questions come. Why do we even study worm observer? There are some questions that motivated me to work in this field. For example, there is large uncertainty in the physical properties and the launching radius of the outflow. We do not know exactly where and how are they produced. We do not know precisely about the chemical evolution of host galaxy and time evolution of black hole. Study of worm observer may provide answers to those questions. Worm observer could be the potential candidates for the feedback mechanism. Until now, I talked about study of worm observer is important to understand about the co-evolution of black holes and host galaxies. But how do we do that? The answers in the most cases are study of photoionization processes of the ambient materials. All the existing photoionization model assumes that the gas is at a statistical equilibrium, but there are conditions where the gas motion results change in the density and pressure on the time scale shorter than the microscopic equilibrium time scale. In this situation, equilibrium supposition is invalid, and current predictions about the worm observer may be far from the reality. Therefore, we need to take time-dependent calculation into account. There are two important time scales. Number one, flow time scales, and number two, recombination time scale. Flow time scale is given by equation number one, where V8 is the wind speed in the unit of 1000 kilometers per second, and M6 is the black hole mass in the unit of 10 to the 6 solar mass. Recombination time scales are inverse of recombination rate and given by this first equation, equation number two. If we plot flow time scale and recombination time scale at different distances from the central black hole, we get like this. Here, the red line represents the flow time scale, and and blue line and green line represent the recombination time scales for various values of atomic number of recombining ions. This shows that recombination time scale is comparable or greater than the flow time scale for much of the parameter space, in particular for lighter ions, higher temperature, and farther from the radiation source. So in this case, we have to take time-dependent calculation, and I will explain how is this done in coming slide. To do the time-dependent photoionization calculation, we must solve three equations of ionization balance, energy balance, and time-dependent radiative transfer self-consistently. If the gas is out of equilibrium, there is change in the number density and given by equation number 2. In the same way, there is imbalance in heating rate and cooling rate. This results in the change in the temperature at different time. To calculate the temperature, we solve the equation number 3. While radiative transfer equation is given by equation number 4, where IE is intensity of radiation field, mu is cosine of the angle with respect to normal, eta and chi are the total emissivity and opacity respectively. Many scientists are working of time-dependent photoionization calculations. I would like to mention few here. Garcia and Oppenheimer and others studied this problem in 2013. Worley-Nat studied time-dependent photoionization in the context of gas cooling from the intergalactic medium to form galaxies in 2007. Time-dependent calculation is computationally challenging, especially in terms of runtime. If we include all relevant ions and labels, it will take days to complete the calculation. So in this case, we must parallelize the code and run in high-performance computing cluster. Perhaps it could be NASA computer cluster. I'm now working in developing the time-dependent photoionization code at TDX star. Once it is completed, we will run this code in AGN environment. In summary, so far we have talked about why do we study water, why do we need time-dependent calculation, and implementing time-dependent photoionization model on warm observers. We also talked briefly about the computational challenges. Thank you very much.
Okay, do we have any questions?
I have one.
Okay, go ahead.
So did you guys like consider any kind of like dust extinction for this ultraluminous, AGN?
We actually do not consider the dust in our gases. It's a kind of, we're developing the code only for, we already developed for purely hydrogen. Now would like to include all other elements up to iron. But now we have not considered the dust in our model.
Okay, and then
yes.
Also, like, do you guys have like observe any like 2175 angstrom bump in your data?
Oh yeah, that you're talking about that line.
So basically, like most of the AGN does show the 2175 angstrom bump.
Oh yeah, right. I'm not actually involved in this kind of dust calculation. We are basically we are in the regime of highly ionized gases. So there's always the point where the dust starts to form, but we are calculating inner side of that region. close to black hole. In fact, accretion phase. People say there doesn't exist dust particle. The experts say that.
So yes, and the last one, and then I'm done.
Yeah.
So basically, like because this is so ultra-luminous galaxy, so I believe that its UV radiation will be very intense.
Sure.
So
Yeah.
so how you expect to survive those dust, like those all molecules nearby?
That's why I told it is purely atomic physics. So we do not deal with dust.
Oh, so okay, so but you talk about some iron.
Oh yeah, there was ionized iron. There was, I guess, 16 times ionized iron. So we are talking
Okay,
high
okay.
temperature field. Yeah.
Oh, maybe I didn't see the 16 part there.
Oh, that's, yeah, maybe that was not clearly delivered. Sorry about that.
All right, thank you.
Other question? From the audience? Dave, yeah, it sounds interesting, and also I would really like to see your simulation data.
Sure.
So I'm sure we'll meet again some other conferences, and good luck on your rest of the work.
Thank you so much.
And yes, great talk. Thank you for your contribution for this session. And with that, I'd also like to thank all the speakers today. Great presentation, great talk. Just some connection issues from Nepal, and we expected that. But we would correct it as we go. And thank you for the great science that you all share. Um, and with that, I'd like to thank ANPA and thank you, Medani, for assisting me. And we'll continue other sessions unless some ANPA members has to say something.
No, we're good here. Thank you, Suman. We're good here. We'll just end this meeting, and members, please go ahead and connect to ACM. It's a separate link that has been emailed to you today morning. We'll see you there. Thank you.
Okay, thank you all. Have a good day, good night, good evening, good morning.
All right, bye-bye.
Thank you, guys.
See you.
मेरा नीचे बंद कर दूंगा
Okay.
फुल शट डाउन कर